Thank you all for coming. As Mr. Hemmati described, we are going to conduct this presentation in English. That is not because I am fluent in English, but we all live in an environment that there are two official languages. One which is easier to handle is English for all of us. So I am practicing my side of the presentation, and I hope you will bear with me if I misuse some words or phrases. In this presentation, I would like to ask you to please ask your questions right on the spot. Wherever you find something that is a question for you or something interesting, please stop me right there and ask your questions. Normally, the question and answering session will go at the end of the presentation, but today I want to try and see if interactive way of communicating in these professional seminars will work. And just for your information, I did a test drive myself last night, and it took me more than 2 hours for this presentation. So please keep in mind that if you ask me too many questions, I would be happy to answer, but probably we will stay here until dawn. So that's up to you how many questions you find interesting to ask me. So the subject of this workshop is about inspection, maintenance, repair, upgrading, and retrofit of existing bridges. Why the title is so long? Because there are so many issues in here that are interconnected to each other. For example, as a bridge engineer, you have an assignment to do inspection for a bridge. But while you do the inspection, you will find out some defects, and you have to do some maintenance or propose some maintenance to the government. And while you are dealing with maintenance, you will find out that some upgrading is needed or some retrofit is needed for the same bridge. It is not logical to do the repairs, for example, right now, and do the upgrading next year. So it doesn't matter where you begin. You might begin by retrofitting of a bridge or maintenance or inspection. You will find yourself wrapped up in all of these issues. There is one question that you might have, is that how important this line of work is. Right now in Ontario, the Ministry of Transportation is handling more than 3,000 bridges. When we are talking about bridges, we are not talking about railway bridges, which are dealt with in other institutions. We are not speaking about bridges that are inside the jurisdiction of cities. And we are not talking about culverts. Normally, bridges under 6 meters of span are called culverts. So there are like 3,000 big bridges under MTO's jurisdiction. And if, as a logical assumption, we say that $100,000 per bridge, which is a quite reasonable number, multiplied by 3,000, it will make $300 billion of investment. So when an institution has something this big, normally they spend, let's say, 0.5% or 0.1% or whatever percentage you might think. That will make a lot of money, in the order of hundreds of millions of dollars per year has to be spent for this kind of work. So this is a big deal, and there is a good market for this. Why do bridges need repair? The reasons are aging, modifications of bridge codes, upgrading of roads and highways, and natural disasters. For aging, the reason for aging is road cycles that we engineers call it fatigue. Most of the bridge components are designed for 2 million cycles of load. But an easy calculation will show you that in a lifespan of 50 years, some components might experience several times that number. So every couple of years, every 10 years, we need to take care of those parts of the bridge who have done their load cycles that we expected from them. And there are also environmental effects. It is moisture, it is changes of the temperature, it is frost action, and all the environmental effects that you are familiar with will either influence components of the bridge or surrounding of the bridge. For example, frost action might not influence bridge directly, but it will influence the foundation or the stability of the slope that the abutment is built on top of the slope. And there is also impact of vehicles. Sometimes people drive their vehicles to the beach for no reason. Sometimes they are intoxicated or not. And about the modifications of bridge codes, I don't need to go into details. You all know that every 5 or 6 years, every code in the business, including those who refer to bridge maintenance or bridge design, changes. So we need to update our bridges, upgrading of roads and highways. Sometimes class of the road changes. We have a lot of rural highways in Ontario. And sometimes a rural highway will change to a provincial highway, or the existing highway. For example, it is a 4-lane highway and it is changed to 6-lane highway. And also proximity to the city. When a bridge is outside the city limits, there are some things that are optional. For example, pedestrian sidewalks. You can put it on the bridge or not. But when it comes inside the city limits, it is mandatory. So we have to do, under the title of upgrading of roads and highways, sometimes proximity to the city forces us to do that. And also, you can see here an example, like, for example, this is a reduced highway, 14.75 meters from curb to curb, and it is changing to the standard, which is 16.75. In other ways, each side of the bridge has to be widened 1 meter. And that 1 meter widening of a structure in philosophy is something like repair or upgrading, because we have to do it side by side the existing bridge. And this is an example of what happens when a 4-lane underpass changes to 6-lane. In this instance, we didn't change the whole structure. What we did was the abutment, which was spilled through, and the earth could come inside the span. We changed it to solid abutment, and with the wing walls and return walls, we hold the earth in back of the abutment and gave it more space here for a 6-lane highway. And there are also natural disasters. You are very well familiar with this one: earthquake, landslide, rockfall, flood, wildfire. As I mentioned, this presentation is very long, so I'm going very fast. And I'm confident that you all follow. And this is an example when a flood comes in and moves foundation. Basically here, the foundation is moved like 1 meter. So the column doesn't work anymore, and it has made a plastic hinge over here. And as a result, the load-bearing capacity of the bridge has reduced, but we don't close the bridge. That is what we do. As engineers who do maintenance and inspection, we don't see it necessary to close the bridge, but reduce the traffic, overpassing traffic to light traffic. And this is an example of when the scour happens. You see the foundation of the bridge is almost exposed in here. Nothing has happened yet. The bridge is working. The piers are solid and it's in their place. But it needs immediate attention because we cannot be sure that when would this whole configuration collapse. Whatever we do with the bridge, it begins with inspection. There are different types of inspection. Regular inspection is mainly visual inspection. There are some tests that we do on regular inspection, but very limited in number and in extent. Normally we don't do a lot of tests like destructive tests or like that. Then there is the comprehensive inspection. In comprehensive inspection, we do order a lot of tests, but most of them should be indestructive and only a few are destructive tests. There is the proof inspection. Proof inspection happens after something big that happens to the bridge. For example, we do upgrading of the bridge for seismic forces. Before the road is under traffic, we have to do a proof inspection to make sure that everything that was as objective of that retrofit has been done. Or whenever a bridge is built for the first time, before giving it to the traffic, a proof inspection should be done. In-depth inspection, we do every test necessary. Sometimes we have to do a lot of destructive tests to make sure that what we are saying is accurate and we have a good understanding of the bridge. There's something very important in this chart, and this is the level of accuracy. The inspector, the engineer in charge of inspection, has to be very conservative. What does it mean? It means that when we do regular inspection and come up with the conclusion that the bridge is safe, it should be 100% safe. We are not allowed to do the slightest bit of assumption. But if we say that under regular inspection, we say that the bridge is probably problematic, maybe by comprehensive inspection we will find out that it is okay. But we have to do comprehensive inspection. And when with the comprehensive inspection, we say that we are not sure about the safety of the bridge, then in-depth inspection will rule out, if the bridge is really safe or not. So in each step of this chart, we should be very conservative or go to the next step. This is the inspection chart of Ontario Ministry of Transportation. They have something called general maintenance inspection. They do it twice a year, before and after the cold season. This is primarily like regular inspection. Then they have the detailed visual inspection, which is comparable to comprehensive inspection, and it happens every 2 years for every bridge. The closest thing to proof inspection, they have emergency inspection, saying that whenever something big happens, something disastrous happens, like a big flood or earthquake, they have to do an emergency inspection. But in essence, it is close to the general definition of proof inspection. And in Ontario, we call it additional investigation, which denotes to in-depth inspection. Whenever we do inspection or deal with a bridge, we benefit from bridge management system, BMS. There are different types of BMS, different types of softwares, different types of doing the job, but in every one of them, these are the minimum information expected. What is important is planning of test combinations. Because the best results come from destructive tests. But those are expensive and they do damage to the structure. These non-destructives are easy to do, cheaper, but less reliable. So one important duty of the engineer in charge of inspection is to design a general scheme of the tests that needs to be a timber bridge. A lot of us think that timber bridge is nothing. It doesn't work, it doesn't. But it is interesting to know that there are some timber bridges in northern Ontario that are working for 100 years right now. And still trucks pass over them. So timber is a very cheap, very easy to handle, very fast to set up kind of construction. There's only one condition. We have to protect it from deterioration. So if it's conveniently covered with the agents that prevent bugs and other harmful things to bother the timber bridges are very common. These are the kind of bridges that are outside the scope of this presentation. Masonry bridges, there are a lot of issues with masonry bridges that in fact if I want to go into details of that, it will need a whole one presentation. So I skip everything related to masonry bridges. Then there are free cantilever bridges, cable stayed bridges, suspended, movable, precast culverts that for obvious reasons do not fit in the category of today's conversations, but any of them have very interesting aspects on their own. These are the common types of defects. Either it is in superstructure, substructure, or this is the bridge. This is the hollow part. Here, the thickness of concrete is minimal. And when you see, can I get it back? And whenever we see these longitudinal cracks, it is probably this type. And these are the tension cracks. This is right where the bridge deck sits on the pier. It is like, this is the bridge and this is the pier, okay? Here we always have negative moment. Here we have negative moment. No matter how much reinforcement we put in here, we always have cracks. But the question is, how big is the crack and is it acceptable or not? So these are typical cracks. These kind of scattered cracks are because of the poor placement and curing of concrete. It has no pattern, no special shape. It will happen because of the poor concrete. This type of cracks that happen here are because of the little covering of the concrete. You know, the reinforcement are very close to the surface, and when the cover is not enough, this type of cracks happen. And this one in here, most of the times happens in skew bridges. This is a skew bridge. Okay? Those type of cracks happen here. Why does it happen? This is the main axis for the bending moment and forces. What is the lateral? It should be perpendicular to the main. Okay? This is the lateral. So when doing this type of bridges, there are reinforcements that go longitudinal like this. And if we put the lateral reinforcement in right position, when we get to here, we have to cut it little by little. The first one comes 20 centimeters smaller, the second one comes 40 centimeters smaller. This is not good for contractor. Contractor likes to do this. This is the longitudinal, and they put the lateral reinforcement diagonal. The important thing is that when you replace this one with this one, you have to add to the reinforcement, because clearly you see that this is not the main plate. You need to have reinforcement on this plate. When you put it this way, you have to add to the reinforcement. So whenever you see this kind of cracks, most of the times it comes to the skew bridges, and that's the reason for that. These are common types of plate cracks.
Yeah, actually, my question is about the rusting. It's very common, and my question, the rust causes some reduction in thickness. I want to know, is there any rule of thumb without going to structural calculation, how much reduction in thickness of flange is acceptable?
Yes. Unfortunately, it is at the end of the presentation, but here what I can tell you is what is very interesting. Most of the steel elements are like this. Either factory made, or we make them with plates in the side, okay? And when rusting happens, it happens all around. So everywhere loses some part of its thickness, okay? What is important is that the weak axis of the structure loses more of its strength than the main axis. Why? Because you know the distance comes with the power of 2, and the area comes with the power of 1. So when we lose some part of this section here, but the distance remains the same, we lose less of the modulus of section as compared to the weak section, that whenever we lose part of it, we lose area, and also we lose distance. So the rule of thumb for evaluating the rusting of a cross section is this. But other than that, you have to go and look at it and measure the thickness of the plates and come up with a solution. And in practical terms, we come up with a reduction factor. Sometimes we say vertical elements have lost 20%. Diagonals have lost 15%, for example. But how do we get to those numbers? It's only one way to do, is to measure. Measure the thickness of the remaining section. Okay, so what we do after finishing the inspection, first of all, we have to understand nature of each defect. I showed you an example of a structural crack in a girder. Sometimes it is not structural. Sometimes it is a structural. Sometimes it is in the deck. Sometimes it is in the pier bend. Sometimes it is in the foundation. So first we have to understand the nature of the defect. Then we go deep and find the source of problem. Sometimes we see a crack in the deck, but the reason for that is the movement of foundation. And why the foundation has moved, it's either the soil weakness or the scouring of the river. So we have to go deep enough to understand the main reason, the deep reason behind what we see in the superstructure. Then after understanding the root of the issue, we have to propose a mathematical model. Then we have to check our mathematical model by showing the status quo of the bridge. Right now, the bridge has a crack in some place and has some tilt in some other place. Our mathematical model should show exactly the location of the crack and the location of the tilt of the foundation. That is how we verify integrity of our model. When the model is approved, then we go and try to extrapolate future. There are two ways, two questions that we want to answer. Number one, what happens if we don't do anything? What will happen if the defect goes on? And another question is, what happens if I put another element, for example, side by side? There is one beam which is weak. I want to put another beam side by side this one. What will happen if I do that? So we want to predict or extrapolate future. Then there might be different repair scenarios. Sometimes we can do something cheap and fast. Sometimes we can do another scenario of repair that goes deeper and fundamental and more expensive. So we have to analyze every possible repair scenario. Then we have to investigate upgrades. For example, in this bridge, we have encountered a structural crack. We are dealing with the crack, but once we are doing the rigorous investigation and planning for the repairs, if the bridge code has changed, it is the good time to implement those changes also. And financial feasibility is very important, because at the end of the day, somebody has to pay for those repairs. And we have to investigate enough to show that the solution that we are proposing is financially sound. And finally, we have to report everything to the proper authority. This is an example of financial feasibility study. This is not the engineer's job. This is a business manager's or accountant's job, but we have to have a general understanding of what happens. For example, in here, we are examining 3 scenarios, option 1, 2, and 3. In option 1, we do some level of repair right now at year 0 at the cost of $600,000. But this doesn't work more than 15 years. This repair doesn't last for more than 15 years. After 15 years, we have to do a fundamental renovation or upgrading or whatever you call it at the cost of $1 million. Then it would be good for 15 years. After 15 years, we have to do some minor repairs because we have done the fundamental job, But anyways, after 15 years of work, we have to do some minor repairs. And after another 15 years, we have to do a little bit more in the amount of $200,000. So in 45 years, in total, we have to pay these monies on these time intervals. Option number 2 is do nothing. Do nothing right now and let the bridge work for another 5 years and get the enough financial resources and get the enough money that we need and do the fundamental repairs after 5 years. Then after 15 years, we have to do the 100,000. Another 15 years, we have to do the 200,000, like option number 1. So in total, we have to do these 3 steps of repairs to have the bridge running for 45 years. In option number 3, we do the rigorous repairs right now. Right now, we pay $1 million, then after 15 years, 100,000, then another 200,000. Then another 15 years, we have to pay another 100,000. There is another important issue, which is the interest rate, or here it says discount rate. Here it says 6%, which is almost double the numbers that we are familiar right now. But whatever the interest rate is, we have to back calculate. For example, in 15 years, we want to pay $1 million. Right now, if we had certain amount of money and it will accrue 6% interest every year, after 15 years, we want to get to $1 million. So we have to back analyze and find out the number for today. Here it says that if we have $417,000 right now and put it in bank with 6% interest, in 15 years it will get to $1 million. So we do similar calculations for every one of these, and the bottom line is that we change every number to show the present value of that number at the year 0, and this is the conclusion. $1 million for option number 1, 790,000 for option number 2, and $1 million for option number 3. So this one is the sound and feasible solution. And we are done with the regular repairs. Now there's another level of repair. We call them substantial repairs. Substantial repair, for example, this girder has shear cracks. Its shear capacity is not enough. We want to add to the shear capacity. This is how we do it. We put stirrups from deck down, then we add a concrete thickness of like at least 2 inches, and these stirrups and the concrete add to the shear strength. This is one general concept of repair. Whenever we have a girder that somehow lost its strength, or we expect more from this girder. For example, changes to the code or changes to the loading capacity of the bridge, etc. One easy way to do is to put pre-stressing tendons in here. You see, what is important is this eccentricity, E sub I2, that multiplied by the forces in these tendons make the resisting moment that we need. This is a section that shows how these tendons go, and obviously there should be some anchors here and here to hold tendons in place. And you see, because this is out of the section, it is very easy to do. This is the same concept. You already know the chain of forces that act here and here, and everything is clear for you. This is the same concept for steel beams. We have anchors near the center line, and we have eccentricity in here that makes the moment that we want to use. The important thing is that here it shouldn't be a pointing corner. It should be somehow tapered because that will damage the strength. This is an example of substantial repair of a huge bridge with pre-stressing tendons. You see, this is a very dangerous situation that pre-stressing tendons of such a bridge, you all know better than me that in pre-stressing technique, everything goes to the pre-stressing tendons. When the tendons are not there, the bridge is not there. So what can we do about this? This is the solution. We cut the part that is deteriorated, then we put sleeves here and here, and there is a coupler knot that we, by tightening the knot, we apply the tension that we need for this tendon. This is exactly what these guys are doing. They're using their trunk, their wrenches, and getting to the exact tensile force that they are using. This is the details of the same technique. We put sleeves here, we press them to have grip, and then these are the couplers, and this is the finished repair couplers. Afterwards, they put forms in there, and once the job is done, only the coloration of the section is visible. This is a substantial repair of foundation. There are a number of techniques for repair of foundations. For example, here I'm showing you the technique of micropiles. In this foundation, there is like 107 micropiles at the distance of 35 centimeters from each other, surrounding the whole foundation. But confining the soil under foundation, we actually give more strength to the subgrade soil, and we manage to make the foundation working.
How much is the depth of micropile?
It depends. Actually, piles are two general types of piles. This is the surface. Okay. Sometimes there is a strong layer like, say, 10 meters deep. Okay. Then we go until we hit the strong layer. But sometimes the strong layer is very deep, like 50 meters or 100 meters. So we only have to rely on skin friction. These are two main types of piles, and depending on which type of pile we are using, we might go until we hit the rock bottom, or go enough to have the friction. And as a person who has done this, I have done this in person, whatever you come up in calculations just gives you a general idea. What is important, when you go and hammer down these piles, for each drop of the hammer, you will get a certain amount of going inside. First, with each hammer, it goes 2 inches, then it goes 1.5, then goes 1. And you have the calculation that shows whenever it gets to the 1/2 inch per blow, that's fine. You have enough strength there. So that's how it works. Whatever we do the calculations, but finally, inside everything would be the same. This is an example of widening a bridge. For widening this bridge, you see the pile cap was until here. Then we had to extend the pile cap to add these new girders in here. and pile cap is, this is the extra section of the pile cap. You see reinforcement, you see ties, you see everything. I don't need to describe this for you. The important things are these nails. These nails are drilled and put into the existing concrete. And afterwards, we have extension of the pier cap, and also we can put more girders and widen the bridge. This is the same thing in reality. You see, these are the existing rebars, these are the new rebars. These are the holes that we make and put stirrups all around. These are time consuming, these are expensive, but when it's needed to be done, it has to be done. Actually, this slide is not about bridge, it is about a structure, building or something, but because of its clarity, I prefer to show you this that shows how we extend the section of reinforced concrete structures. This is similar situation by using of pre-stressing tendons. You see, pre-stressing tendons, because of their huge tensile capacity, help us in so many ways. This is one way to do extension of a bridge. It was here, and we have extended here. We have two bearing plates in here for two extra girders, and we can widen the existing bridge. This is another example of a steel bridge. This was the last girder, and this was the end of the deck. Now we have expansion to here, another girder, another splice of the cross girder and stringers and everything. We can add like 21 foot of widening in here. This is another example, similar concept, similar situation, a little bit different in details. I will not go into details for you. This is how we do with simpler situations. This is the existing slab bridge. We are extending this much, like 1 meter or so. So the easiest way to do is, these are precast slabs that have enough rigidity to cover the span, and only this rebar is drilled and put inside the existing part of the deck. And you see, from the architectural point of view, when you look at the bridge from this side, you will not see a lot of discoloration or change, because you see this that's covering up everything else. This is similar situation. Another way of dealing with the issue, this is a box girder, pre-fabricated and put in place. Now we go to the section of updating and retrofit of bridges. In retrofit of bridges, we actually, it's not enough for us to go to the previously built stage of the bridge. We want to add something to its integrity or expecting more resistance. So how do we do that? We either do jacketing of columns by steels or spiral confinement of columns. You know that when the confinement grows, the axial capacity of the column will grow. So by adding confinement, we make the same cross-section of the column to bear more load. FRP confinement of columns. Span reduction is one solution. Post-tensioning, I have already spoken about. Add some stringers or beams, and steel plate or channel reinforcement afterwards. These are the techniques normally used for strengthening of columns, either reinforced concrete jacketing, or using steel plates for jacketing, or using FRP jacketing. This is an example of what happens. This is the existing column. We put grout and spirals or whatever that we need to add to this column section, and on the outer skin is a steel casing that both keeps everything together and also by its cross section adds to the bearing capacity of the column. This is an example of an actual jacketing of a column. It is crude, it is not beautiful, but it is exactly how it happens. You see, these bolts and nuts show that these ties have gone inside the structure, and those plates are adding to the integrity and modulus section of the column. And this is an example of FRP reinforcing of girders. FRP, in practical terms, does give the same qualities that steel normally gives, and it is easy to use, easy to put together with the existing membrane, and people like to use FRPs. And this is FRP jacketing used for columns. This is when we add another element for strengthening. Right now there are two girders in here. We add a third girder and change the configuration of the bracing, so we have extra externals in here. This is a very common way of strengthening trusses. You see, the first one, by adding these pre-stressing tendons, in practical terms, we are reducing the span from this length to from here to here. The span of the truss is reduced. In here, by putting pretension on these cables, we are adding to the flexural strength of the midsection of the truss. In here, we are transferring a huge part of the load from midsection directly to the abutment. And this solution is an extension of this solution with extra eccentricity that adds to the value of the pre-stressing time. And after considering every possibility that we already talked about, those were from technical points of view. But there are also traffic issues. You cannot do everything you want to do in every place. For example, the issue of repairing the McDonald freeway in Lakeshore area is for more than 10 years on the table, and nobody can tackle it because nobody can shut down the bridge. You know, the main problem is that nobody can shut down the bridge. There are financial issues that I talked about. There are heritage values. There are some bridges that are so important, so historically or prestigiously important, that the government is ready to put 3 times the value of a whole new bridge, but to keep that one the same as it is. And there are environmental issues. Sometimes you want to do concreting to strengthen a bridge pier, but it is inside a river, and you cannot contaminate the river. It is the place that the salmon reproduces, etc., and you have to come up with another solution because simply you cannot do concreting inside the river. And there are always political and social and obviously military value. Sometimes the bridge is used by military, for example, for movement of tanks and heavy artillery. So you have to take into account that usage as well. This is an example of traffic issues when we are dealing with repairs of the bridge. This is exactly the location that me and Mr. Bakhtiari were talking about in Bathurst, and it was a mess for 1 whole year. Reduced to 1 lane, and there was a lot of problems. This is an example of heritage. This bridge is in Iran. It is masonry bridge. It is very thin, very tall, in a horizontal curve. The curve is not circle, it is spiral. And it is built in the World War II. 70 years ago, masons and people like masons built this bridge in an area which is very active from seismic point of view. It is in the middle of the Lorestan area. So we are ready to put any money needed just to keep it the way it is. For example, if we want to strengthen this main span, we cannot say, okay, let's put a steel girder in there and solve the problem. No, we cannot do that. So this is the heritage map. These are the codes and standards that normally we use. OSIM is the Bible of this type of work, and also the Highway Bridge Design Code. And these are mainly other codes and specifications dealing with structure, rehabilitation, concrete, etc. And other than these, almost every code that we have in Canadian standards applies to our work, because either you are using a chemical, or you're using a certain type of test, or you're using a certain type of modification. So almost every code in the system applies to our work. Now I'm getting to case studies. We have half an hour left. Yes, I will go fast. But thank you very much for not asking me the questions, because otherwise you have to go. Okay, case studies. This is a bridge that I inspected myself. This is the Waterloo area north of Kitchener, and this is the location of bridge on Conestoga River. And this is my stamp showing that I did it myself. That's the bridge, and that's the Conestoga River. And this is the structure system of bridge. You see it has a skew angle of 43 degrees. You know, the degree of skew is very high. And it is slab on girder bridge. So in other words, there are no shearing elements here to put together the slab and the girders. This is what I talked about the corrosion of steel sections. You see the greatest loss is around the weak section, Y section. This is the estimation of the reduction of capacity. There is 20%, 50%, 45%. And as I told you, there is no way around it. You have to go there and measure it one by one and come up with a solution. This is part of the abutment. You see how the concrete has deteriorated. Also, there are some rusting of the steel sections. This is the soffit of the deck, and you see that concrete has delaminated and the rebars are exposed and also rusted. This is also a section of the bridge. Rusting has happened, and You see everything clearly here. This is the area of impact. You see that a truck has hit the cross bracing of the bridge, and it is something very considerable that has changed the configuration of the bridge. This is another example of rivets. You know, 50 years ago, most of the bridges were built by rivets, not by welding, not even by bolts and screws. Yes. So this is an example of that. And finally,
what is the problem with rivet?
they were beginning to rust.
Oh, for rust.
All the rivets and the surrounding area. And this is what was the final solution. You know, because this is a very narrow bridge in a rural area. Nobody wanted to put a lot of money in there. So the solution was to reduce the servicing of the bridge. Loads are reduced to 21 tons, and if it's a truck trailer, to 29. So this was a case study of inspection of bridge.
Sorry, regarding to rivet, are they getting loose after?
It depends on the depth of the rusting. You know? If you take care of the rusting on earlier stages,
By fatigue, the rivet is getting loose or no?
no. In this bridge, there was no side effects of fatigue.
If any problem, can we replace with bolt, for example?
You can, but before doing that, you have to inspect the surrounding of the hole.
Oh.
You know, this is how the structure is designed. This is the hole, and this is the bolt or rivet. Okay. Normally, the material of rivet or bolt is higher quality than the base plate. So, if anything happens, it would be around them. So, if there is a problem that has caused the rivet to loosen, first thing you have to check is the surrounding area. Is it in its standard shape or not? Most of the times not. And then you can cut these rivets here, put another plate, do a new hole, and put the new screw in there. That's how you can fix the whole problem. But just by changing the rivet, I told you, you have to always go to the root of the problem. Yeah. Just by replacing this one, we cannot be sure about the other parts. This is an example about sizing retrofitting. For liability reasons, I cannot tell you about the location, even though you might recognize it. So this is the bridge in its original shape. It was very old, very rusted. It has every problem that I already spoke about. For example, you see here, this is impact of a strong truck on one of the columns, and also seepage of water from deck to girders to column bends, and everywhere in the bridge there was impact. This is another problem with the bridge. Not only there is seepage of water in here, you see that the sitting length is not enough. In a highly seismic area, let's consider that we have strengthened this whole column bend, and we have fixed every other problem. There is simply the question of dropping down, because the sitting is not long enough. And if you look at the whole configuration, you see that the sitting is small, the girder is tiny, and the cross section of the column was only 0.8 meters, 80 centimeters, the section of the column. So in a highly seismic area, if we fix everything else, the columns cannot bear this amount of load, and we have to strengthen the columns. And we strengthen the columns, the force goes to foundation, but the foundation is not strong enough. So you have to strengthen the foundation. And when there is a highway passing underneath, that would be a nightmare. To go deep under the foundation, fix the foundation, then fix the column, then come up to the deck. So this was the whole configuration. But what we did, we think outside the box. We said, I said, we cannot go under the foundation in this crowded freeway. We cannot fix these columns and these girders properly, and we cannot give enough seating in here. What shall we do? Change the whole configuration of the bridge. Bridge was like this. Three simple spans. And there was here, column here, and there was a column here. What we did, we put these parts together and made the whole deck a continuous deck. By doing this, the seating of here became irrelevant. It doesn't matter anymore how much seating we have. And because the plan of the bridge was like this. This is the plan of the bridge. When the seismic forces acted, we had forces in here that columns were supposed to take these huge forces. By putting these together, we have a monolithic deck deep enough to have rigidity, so we can put every force that we have here and here. We don't need columns to do anything for us. So we didn't have to do anything in here to have conflict with the traffic, and we put every force in the abutment. Abutment is normally in the sidewalk. So we had much easier task to do.
But you have changed the moment distribution of the day.
Exactly, exactly. Thank you.
Sorry, I have a question. Do you have any record about analyzes the structure before, like maybe 50 years ago?
Yeah.
Nothing? No reference? Because if you want to change the structure,
Yeah.
you have to remodel the bridge and put the influence line and just analyze. I think you need more records about that bridge.
Yes, that would be very helpful. What would you do if you don't have anything?
No record in Ministry of Transport.
No, nothing. The plans that I already showed you about the location of the tests refer to the same bridge. We did some very special tests just to have an idea about the strength of the materials. But we couldn't go inside the girders because by looking at the depth of the deck, I had an understanding that probably the girders were pre-stressed. So going into a section with pre-stressing tendons but was very risky. I didn't want to jeopardize the integrity of the bridge. So we were dealing with a puzzle that parts of the puzzle was not defined for us. So what we did was exactly what Mr. Ghaffari mentioned. Let's go. Five minutes. Okay. Well, I can finish right now. This is the plan of the bridge. These are the locations of the surveyors that I just mentioned. Those are very important. That shows us how much have these structures changed as compared to the surroundings. This is the cross-section of the bridge configuration that I just talked to you about. What we did was to monolithicize these parts of the deck, and this is what Mr. Ghaffari mentioned. This graph is not about this bridge, but this is a similar bridge that can do for us. This is something similar to the moment distribution of the original bridge. We have 0 moment capacity here and there, and maximum in the middle. But if we make it monolithic, we will have some amount of negative moment capacity in here, and then it will reduce the positive moment of the midspan. In this way, I didn't need to know the specifications of the girders. Whatever the specification was. Right now, it was having this much capacity. I was reducing it this much. For no doubt, it would work better. So the question was, how can we get enough negative moment around the joints? This is what we did. We poured concrete in between the two girders, and we made holes in there and put pre-stressing tendons beginning from center line and going all the way near the soffit of the deck to make as much eccentricity as we could. This is how it was done. This is the pattern that they use for doing the holes and putting the bolts in. And after doing that, you see that these are the plates bolted to the existing concrete. And this is the anchoring area of the pre-stressing tendons. And these are stiffeners to strengthen the whole configuration. Now you see that these are the holes inside this is the pier cap. These are the holes that go through, and these are the tendons that have been anchored in here. These are the finished product. You can see the plates. You can see some dislocations. These locations are not very straightforward. Why? Because sometimes they hit an important rebar and change the location. So this is the type of problems that we face while doing the actual job site. And this is the final, all capped and covered and painted and everything in place. And this is why they were doing the columns. Anyways, we had to do some repairs on the columns, although we didn't want that extra strength, but we had to do. These are the details of, these are exploratory cuttings in here to find out about the size of the rebars, the spacing of the stirrups. So we were not totally blind, but we didn't have as much information as we needed. This is the finished product after covering up everything and after finishing the piers. And this is the abutment. The same problem of sitting lengths existed also in the abutment. We put these steel membranes here to put extra sitting lengths at abutment. Also, abutments now are facing with huge horizontal forces that I described here. The whole bridge is supposed to be restricted here. So, no way these foundations could bear the forces that we needed. We put new piles and new elements. And in this way, we made the abutments structurally strong enough to hold the whole forces. This is the details of the diagonal section of the abutment. This is a better view of the sections and going from corner of the girder and abutment column. And that's it.
Thank you.
How long did it take for repair this bridge?
The execution, about 6 months.
How much time?
I was not doing the repairs, I was the consultant. I gave the designs, but for your information,